Hello and welcome to York Observatory monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We're broadcasting live from the AICO Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time here on our YouTube channel, YorkU Observatory. For any questions or comments you have for our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Instagram with the handle at York Observatory and Facebook at Alana Carfell Ops. I would like to inform you about the opening and call for applications for a summer 2024 Astronomer in Residence program. This program is a collaboration of the Allen I. Carswell Observatory with Killarney Park to host astronomers in the certified dark sky side of Killarney to lead in-person presentations and shows using the park's observatory. To learn more about the program, its requirements, and the application process, visit our website at yorku.ca/science/observatory/air. Good evening, everyone. I'm Camila, and I'm here with Dr. Alireza, Paul, Zach, Hector, and Deb. We're here from the Allen I. Observatory at York University. Tonight, we're joined by a special guest, Dr. Naji, who will be talking all about the sun. But first, I would like to mention that the observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Toronto has been caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous people. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts showing the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area.
Hello, everyone. I'm Paul, and I'm a second-year astronomy and physics student at York University. I'd like to talk to you about what's up tonight and what we can look forward to in the month of August, because that's the period covered between this TeleTube and the next one. So we've had an absence of planets in the night sky since the mid-spring, I think, but they're starting to come back. And if we go out tonight, if you go out and look kind of east around 2 a.m., 2:30 a.m., you're going to see something like this. So you're going to see that Saturn is just to the right-hand side of the moon, slightly above it. And that you'll also notice a very bright star, it's a planet actually, Jupiter, just on the horizon. And slightly to the right of that and above it would be Mars. There's also Uranus there, but you would need a telescope or binoculars and good seeing conditions to see it. Just above Uranus is the Pleiades, which is our first hint that unfortunately summer is starting to see its end as we move into the winter. The Pleiades is in Taurus, it rises in the sky, and it becomes one of the dominant late fall and winter constellations. Going to the next slide, August also is star party season. So star parties are basically get-togethers of astronomy enthusiasts, and they bring their telescopes and their cameras, and they generally have talks and things like this, but tons of observing. And we see a lot of them in the month of August. There's many of them all over the world. But in the Northern Hemisphere, August is the predominant time for it. And associated with that is the Perseid meteor shower. And Perseid meteor shower is basically Earth moving through the remains of the tail of a comet. So a lot of particles are ejected into the upper atmosphere. They heat up, they burn up, and they leave trails. Now, on any given night, you can look at any section of the sky and see approximately 7 meteors an hour. That's kind of normal, shooting stars. But during a meteor shower, we've got these concentrations happening. And if the sky is clear and it's dark and you've got good seeing conditions with no light pollution and the moon has already set or hasn't risen yet, you could see up to hundreds an hour, but certainly a couple every minute. So to find Perseus in the night sky, you would look sort of between north and east. Around this image is around 2 o'clock in the morning, and on the 12th, which is when this is set for, you would notice a very bright star. We'll talk about that in a moment. But just to the left of it and above it would be Perseus, and that's the center of where the meteor shower is going to come. Now, that bright star we talked about is actually two planets. Mars and Jupiter are going to be in conjunction, which means they're going to be very close together. In fact, they will skim each other if you can look at them through a telescope. That only lasts for a few seconds, but you will get a very bright object in the sky at that time. And coincident with that, this is the 12th, but from the 8th to the 11th is Starfest 2024, which is a very well-attended Ontario star party. And you can go to just Google Starfest 2024. You can sign up to go. They have camping available and there's hotels nearby. It's not really recommended for day trips, but you can do that if you wish. Although you can't really leave once it starts because they want to maintain dark sky conditions. So, you would be there for the night, but it's certainly worth attending. And I will tell you that several people, myself included, who are on this TeleTube tonight will be in attendance there. So we certainly hope that you'll say hi to us if you drop by. And with that, I'll turn this back over to my colleagues, and I wish you good observing in the month of August.
Hello, everyone. I'm Dr. Rafiee. I'm a senior lecturer at York University, and I'm happy to introduce our speaker, Dr. Majid Naji, for tonight. Dr. Majid Naji holds a Bachelor of Science in Applied Physics from the University of Isfahan, Iran, and a Master of Science and a PhD in Electrical Engineering Photonics from the University of Laval and the University of Ottawa. Since 2019, Dr. Naji has been a senior scientist at OZ Optics Ltd, where he works with femtosecond laser systems to write waveguides inside fiber optics, creating various fiber sensors and components. Dr. Naji has been passionate about astronomy since his teenage years, and he has been actively involved in many amateur astronomical activities. His main interests and activities in astronomy include sun and solar activities and their effects on satellite performances, which we will hear about them tonight, atmospheric turbulences and seeing effects, and measuring seeing, astronomical interferometry, building simple astronomical apparatus, spatially small telescopes, night sky observations, history of astronomy, and astronomical photography. During the recent solar eclipse on April 8, 2024, Dr. Naji initiated and led a project to measure the Moon-Earth distance using the Hipparcos method, collaborating with 7 teams of other astronomers. Additionally, he has translated, edited, and published a night sky atlas and authored 4 astronomical articles. We are very happy to have you tonight in our show, and please take it away.
Thank you very much, Dr. Rafiee. It's my great pleasure to be with you and have this opportunity to have a short presentation about the sun and the sun activities. And let me share my windows. Give me a second, please. Yes, hi. So let's say hi, everyone. Thank you very much to give me this opportunity to be with you. And let me have some discussion and share my presentation about the inspiring sun. For tonight, for this presentation, I have, let's say, 5 sections. The first section, I'm going to go through the sun in our legend to see what's the sun position in the different cultural legends. And after, we go and discuss about, what is the sun exactly, especially talks about the sun's interior and the sun atmosphere. At the end, I am going to discuss about the sun-earth connection, especially the space weather. So, I will start with the sun in our legends. So, as you know, sun has a very important position in all cultural legends. In different cultures, you can see the trace of the sun as a god most of the time. So the first one would be, the most famous one would be Apollo. It's the sun god for the Greek and Roman. For ancient Egypt, for Egyptian also, the ancient Egyptian also, sun has a special roles, especially as a Re. Re was the sun god and the creator for the ancient Egyptian, and you can see, let's say, his picture everywhere in most of the Egyptian, let's say, architecture, especially ancient Egyptian architecture. Surya was the sun god also for Hindus. He was a man with the red man with the 3 eyes, 4 arms, and riding a chariot with the 7 horses. For the Mesopotamia, Shamash or Utu was one of the sun god, which still you can see his trace in the current Mesopotamian culture and the countries. Celts has their own sun god. They call it Lu. Chinese has 10 godless. This is 10 suns. In the ancient, based on the ancient Chinese legend, because in Chinese they have a week of the 10 days, and in ancient time they assigned 1 sun to each day. However, based on some legend, one emperor asked those suns to not come all of them to the sky simultaneously, but they don't listen, and therefore an archer shoot 9 of them, and just the sun remained for right now. Aztec also had 4 suns before our current sun, based on the legend, and the current sun which they had as a sun god, Tonatu, is the 5th sun which they have. Incas also had their own sun, call it Inti. And the indigenous Navajo indigenous also, they have their own sun god, which carried every day at the back of the horse, and the night goes to the let's say to rest and hang on in the house. One of the famous sun god was Mitra. Mitra was the sun god in the, let's say, among Roman and the ancient Iranian. He was the god of the oath, justice, and as well as light. And still his name and his traces exist. Sorry. One of the famous, let's say, iconography of the Mitra, which still you can find those icons in most part of the Europe, is the Tructony. Tructony is a very famous icon which shows that Mitra killing a bull. And there were lots of story and debate based on the meaning of those this icon. But one of the recent hypotheses about this icon back to some kind of the astronomical, let's say, effect, and that one is the axial precision of the Earth. So as you know, because of the axial precision of the Earth, the location of the vernal equinox and the zodiac region changed over time, something over 2,000 years time, let's say. So about 4,000 years ago, that point, that vernal equinox point, was in the constellation of Taurus. But because of the precision, about 4,000 years ago, that point started to move to the constellation of Aries. And for those who believe on the sun, let's say the ancient Mitraic people, so they said, okay, right? The god somehow turn his face turn off his face and don't look at the Taurus, and therefore they pick it up that one as some kind of the interpretation of the sun, or let's say Mitra, or the god who's killed the Taurus. Maybe another thing which we should inspiration about the sun, which we should say, is that back to the modern time. So as you know that Galileo, the Italian scientist, let's say, he was the first man who systematically recorded and observed sun and the sunspots. So based on his observation, he found that there are some small dots, or let's say black dots, on the surface of the sun. And also he found that the sun is rotating. So therefore he came up to two hypotheses. One of them is that, okay, sun is not stationary, it's rotating. And the other thing is that, okay, sun is not perfect, because based on the ancient, especially Aristotelian notion, all the heaven, everything above the earth is immutable. It's somehow, let's say, spotless, and should be spotless. And therefore, that kind of the idea and observation which Galileo has, and as I mentioned, the solar observation somehow contest that kind of the notion, and causes a big revolution, let's say, in our view toward the heaven and toward the, let's say, cosmos. But let's see what's exactly the sun, because talk about the sun in the let's say, in the legend, in the different culture, even the modern culture, so say, when we go with the Galileo. But let's see what's the sun exactly. So sun is an ordinary, let's say, star among the 10 billion stars of the Milky Way. So Milky Way has something about 10 billion stars, and the sun is one of them. Sun is located in one of the arms of the let's say Milky Way, which we call it Orion arms, sorry. And let's say Milky Way also is one of the galaxies among the approximately, let's say, 200 billion galaxies in the universe. So we can say sun somehow approximately is one of the stars among to the 10 to the power 22 stars, something like that, 10 with the 22 0 in front of it. So it's, let's say, it's nothing in the universe, but for us it's very important. The sun age is about 4 and 6 billion years. So it's somehow right now is the middle age star. It's in the middle of the also a diagram which we call it Hertzsprung-Russell diagram. The radius of the sun is about 109 times than the Earth. Its volume is about 1,300,000 times of the Earth. Its mass is about around say 300,000 times of the Earth, and it consists of more than 99% of the solar system. So in solar system, less than 1% of the mass let's say distributed to other planets. More than 99% of the mass is belong to the sun. So let's have something about the sunlight. Let me display this thing. It doesn't have the sun right now, but
like all stars in the universe, the sun is not immortal. The sun was born 4.57 billion years ago. It survives by burning 600 million tons of hydrogen atoms into helium atoms in its core every second. However, there is only a finite amount of hydrogen in the core of the sun. For the next 4 billion years, the sun will continue to fuse hydrogen to make helium. As more helium builds up, the core will shrink. As a result, nuclear fusion reactions accelerate. Faster fusion means more energy output. In 3.5 billion years, the sun will shine 40% brighter than today. At this point, Earth's oceans will boil, and the ice caps will permanently melt. All the moisture in the atmosphere will be lost. Life will not likely survive, and Earth will become brutally hot and dry, like Venus. After that, the situation gets worse. 5.4 billion years from now, the sun will exhaust all hydrogen in its core. The core will heat up and get extremely dense, but the sun's outer layer will expand a lot. It could expand big enough to swallow Mercury, Venus, and maybe even Earth. Even if it doesn't grow as far as the Earth, high temperatures will completely burn our planet. Once the sun has emptied its fuel reserves, it will become unstable, and as a result, it will begin to pulse. Each pulse will remove more of the sun's mass until all that's left is a cool, dense core. This core is called a white dwarf. The sun will spend the rest of its days as a white dwarf, slowly cooling and dimming as time passes. By this point, Earth will be completely inhospitable.
Oh, okay, so as it explained, right now sun is located here in the let's say Hertzsprung-Russell diagram. After about 4 billion years, the sun would burn most of the let's say hydrogen is in its core, and therefore it's become something which we call it the red giant, a very big one, which at that time all the life in the earth would be gone, and after it will back and come down and become something which we call it white dwarf. So let's see what's the sun exactly, what's the structure of the sun exactly. So we can somehow, let's say, divided the sun structure to two parts. One of them is the interior of the sun, and the other one is the atmosphere of the sun. So the sun interior consists of the three parts or three layers. One of them is core, which most of those nuclear fusion happen at there. Another one is radiation zone, and another one is convection zone. So in the core of the sun, the temperature is about 15 million degrees Celsius or Kelvin. Most of the scientific temperatures expressed in the degree of Kelvin, but when it's come to the something like more than 1,000 degree of Kelvin, the Kelvin and the Celsius would be somehow similar, so not very different. So that's why I'm using the Celsius, because it's more touchable for most of the people. So the temperature is about 15 million Kelvin. Its density the density at the core is about 150 grams per square centimeter, something like 150 times more than the density of the water. It consists of the 50% half, or let's say half of the mass of the sun. So most of the sun is there, and the radius of the core is about 0.25 or 25% of the radius of the total radius of the sun. At the core, 4 proton or 4, let's say, hydrogen atoms fuse together and generate a helium. And through this nuclear fusion, they lost something like 0.71% of the original mass. That mass, based on the famous formula which most of us know, is that E equal to mc2. M is the mass, and the c is the velocity of the light to the power 2. So that mass converted to the energy, which mostly kinetic energy and let's say gamma rays and some other particle products. So in each second, sun, let's say, converted 6 million tons of the hydrogen to helium and lost something about 4.2 million tons of the mass. That 4.2 of the mass, as I mentioned, is converted to energy and generates something like 384 septillion watt of energy. That energy is equal, so the 1 second energy generated in the sun, equal to somehow 600,000 years of the current global energy which we have. So it's equal. So that one is equal to 1 second of the energy generated in the sun could be enough for let's say 100,000 years of the energy which we use right now. Something which is also interesting to know about the sun, those kind of let's say energy production or energy generation inside of the sun is very small. It's very slow. It's not very fast. So the lesser density of energy which generated inside of the sun is something like 276 watt per cubic meter. So each cubic meter in the core of the sun, if you go by the volume, generates something like 275 watt of energy. But it may be interesting to know that the power density or generation of the density inside of the human body is about 1000 watt per square centimeter. On the other hand, the rate of the generation of energy in our body is something like 4 times more than the rate of the generation of the energy inside of the sun. The next layer of the sun, the sun core interior of the sun, is the radiation zone, which is between 0.2 to 0.7 of the radius of the sun, or 20% to 70% of the sun radius. It consists of the 48% of the sun mass. In the radiation zone, the energy which generated inside of the core transfer or move by mean of the radiation. But it's not a very fast also processes. It takes about 100, it's based on some models. They said, okay, it takes about 170,000 years for a photon to be generated inside of the core to reach the end of the radiation zone. On the other hand, the heat which we received, for example, today from the sun, generated more than, let's say, 1,700 years ago. I mean, before even the human civilization inside the core of the sun. The next layer of the, let's say, sun, interior of the sun, we call it convection zone. So the convection zone is started after 70% of the sun radius. So it's started after. So if we move from the core, so from the 0 to about 20%, we'll have the core where the energy is generated. After from the 20% to 70% of the radius, this distance, we come to the somewhere which we call the radiation let's say, zone, which as you can see, most of the sun energy travel in the zigzag let's say paths, and they travel inside of the sun by mean of the radiation. And after we reach to the another layer of the sun, which we call it convection zone. So in the convection zone, the temperature of the sun somehow do not drop to something around 2 million degrees Celsius. So around 2 million degrees Celsius, some heavier element inside of the sun could bond or could absorb the electrons, and especially some metals especially. And it caused that those regions become somehow opaque. So when it's become opaque, the sun cannot, the energy cannot travel inside of this region by mean of the radiation. So somehow the energy trapped in the lower layer. And since it's trapped, it start to go to the higher level, or let's say go to the higher, to the surface of the sun through a convection. Convection method, which somehow like the boiling of the water. So it starts, let's say, it's start to boil inside of the sun. This layer consists of about 2% of the sun mass. So as I mentioned, so in this, because this layer is somehow opaque to the light, so the plasma have to boil, have to move. So it's happened like that. The hot plasma goes up to the surface of the sun. After at the surface get cold, and after back again goes down, because the intensity is changed to the higher intensity when it gets cold. The region, the small region, or the cell on which we have this kind of the boiling, we call it granules. So granules are the convection cells, which carries the sun energy from the bottom of the convection zone to the lower, to the higher level, or to the surface of the sun. Each granule has a dimension of about 350 kilometer by 350 kilometer. The amount of the energy which convey through those granules, we can see also in the real photo here, those small granules. It's about 3 years of the energy which generated by a big dam like the Hoover Dam. So lots of energy, travel through this granule, those small regions. There's something like 13, because I did a small calculation, I found that something like less than a minute of the energy which travel or which come to this small region of sun or granule of the sun is equal to 1 year consumption of energy of Canada. So if we have the energy, if we can harness that small region energy for less than a minute, we could have, feed Canada for for about 1 year. So I maybe jump this part is about the anatomy of the sun, because I'm going to save more times, and come to the next slide. So one of the questions which may come to the mind that, okay, how we know about the core, how we know about the radiation zone, and how we know about the, let's see, convection zone. So one of the methods which we use to study the sun and interior of the sun to come up with those numbers which I share with you is that helioseismology. So by helioseismology, by studying the waves which let's say travel inside of the sun and manifest themselves in the surface of the sun, we can, by studying them and the modeling them, we can discuss and we can let's say do some modeling, and we can find that, okay, what happened inside of the core of the sun, or what happened in other layer of the sun. Exactly like what we do with the Earth, because we know about the Earth layer by studying the seismic waves which generated or which propagated on the surface of the Earth. This one is a very nice example. For example, this is the photo which was taken by SOHO satellite, this solar study satellite. It shows that how let's say a wave, some kind of the seismic wave, generated because of the flares explosion happening. So a flare explosion happened on the surface of the sun, and that explosion, like an earthquake, generates a lot of energy, and that energy is causing some kind of the seismic wave which propagate on the surface of the sun. So by studying and recording those propagation or those waves and the shape and they form, scientists could come up with some kind of the models, and they discuss and talk about the sun interior. So usually when we are going to talk about the sun interior, we do a couple of methods. One of them is observing, so measuring its mass, that's the surface temperature, spectrum, magnetic field, which I'm going to discuss about it. Other one is the solar oscillation, or solar, let's say, seismology, and the other one is that the solar neutrino, because during those nuclear fission also inside of the sun, fusion inside of the sun, some neutrinos also generated, and by counting those neutrinos, we can somehow verify the modeling which we have, computer modeling which we have about the sun. And the last one is the computer modeling. So most of those numbers comes from those computer modeling. Okay, the next part of the sun, which is very interesting for most of us, is the sun atmosphere. Sun has 3 layers of atmosphere: photosphere, chromosphere, and corona. So photosphere is the layer or the atmosphere which most of us or all of us can see every day during the daily life. So that one is the bright layer, generates a lot of heat and energy, and has a spectrum. This spectrum is more like the black body radiation spectrum, we call it. And when it reaches to the Earth, because of some atmospheric absorption, has some kind of the line inside, absorption line. The thickness of this photosphere is about 300 kilometers, so it's not very thick. And as I mentioned, it's the layer which all of us could see. When we have the spectrum of the sun, the visible spectrum of the sun is like this, and as I mentioned, it's more like the black body radiation. We see a lot of dark line or absorption line, which we call them Fraunhofer lines inside of that layer, and this happened because of the absorption of the other elements which are exist in the sun atmosphere. One of the famous or one of the most important feature of that atmosphere, that layer, is that the sunspot. So in the photosphere, so sunspot is the dark spot or dark spot which we see on the surface of the photosphere. So if you have a chance to look at the sun through a safe solar filter, we'll see most of the time, depend on the time, but most of the time we could see some small dots on the surface of the sun. Those dots are the darker, this is the cooler region, which has a temperature of about 3,000 to 4,000 to 4,000 and half, 4,000 and 4,500 degree Kelvin. Usually they have a lifetime. So as I mentioned, they are not permanent. The lifetime is something between 1 to 100 days. And they are the magnetically active region on the surface of the sun. Those sunspots has a period, so the number of those sunspots increase and decrease, and that increasing and decreasing has a period of about on average of 11 years. So yeah, they are the active magnetic region on the sun, which we are going to discuss about it later, and it's happening because of something which we call the dynamo effect. Those magnetic regions, those sunspots, also they are bipolar. So if I'm back to the previous slide, so exactly they are like a magnet. They have the south-seeking and the north-seeking poles, and we can, by doing some kind of the magnetophotography or magnetic photography of the sun, we can see and we can confirm that those sunspots are bipolar, consists of the, let's say, N, which is the bar, the bright or white region, and the south-seeking, which are the dark region in this picture. As I mentioned, they have the they have a period, those sunspots. So the number of sunspots and the location on the surface of the sun change over time. They have some kind of the 11 years period, and they are recorded and observed since the time of the Galileo, but the most, say, for more reliable map which we have back to about less than 200 years ago. Right now we are near the solar maximum, so we are in 2014, we are going to go to 2015, so we are going to be near the solar maximum. It means that when we have the most amount of the solar activities and the sunspot. So let me do this thing, would be nice.
From relatively minor interruptions that create sunspots to massive surges that drive solar storms, change is one of the few constants on the sun's surface. So, what's behind all this variability? The short answer is magnetism. More precisely, it's the shifting and twisting magnetic fields seething below the sun's surface. Like Earth, the sun has north and south magnetic poles, with magnetic field lines connecting the two. At times, these field lines follow neat vertical paths between the northern and southern hemispheres, but that's the exception more than the rule. More often, the motion of plasma inside the sun mixes up the neatly organized field lines. This is because plasma spins faster at the equator than near the poles, a difference that causes the lines to stretch. At the same time, swirling currents in the convective zone twist the field lines and cause them to kink upward. What's more, all the stress and strain generated by these two forces actually strengthens the magnetic field rather than weakening it.
Imagine this spring is a magnetic field line. The magnetic field inside the sun is amplified, is strengthened by the rotating motions and the shearing motions and the churning motions inside the sun. It wants to expand upwards, and it does, until it pokes out through the surface of the sun.
As magnetic field lines emerge, they form loops. Where they break through the surface, they temporarily divert the upward flow of hot plasma and create the relatively cool, dark regions that we know as sunspots. But the effects can be more than cosmetic. Often extending far above the sun's surface, the magnetic loops continue to be twisted by the currents beneath. Sometimes the field lines twist enough to cross. The resulting magnetic reconnection, similar to a short circuit, heats the surrounding plasma to tens of millions of degrees. This unleashes a solar flare, a powerful burst of energy and particles that can have disastrous results if directed toward Earth. Sometimes, the energy released by these magnetic reconnections produces another type of solar storm. Coronal mass ejections, or
Okay, so sorry, I stop because I'm going to go through all those details. So the next layer of the sun is the chromosphere. So chromosphere is the second layer of the sun. Try to be a little faster for this part. It's something between 300 kilometers to 10,000 kilometers above the photosphere. As I mentioned, because of the solar magnetic activities, that region is a little hotter, even more than a little hotter than the photosphere, and its temperature is something about 20,000 degrees of Kelvin. Usually this region of the sun, or this part of the atmosphere, we can see during the solar eclipse, especially at the second and the third contact time, if we have a chance to be somewhere which we have a totality. So these small dots which we can see, those belong to the chromosphere, or using a specific filter which we call it H-alpha filter, which allow the H-alpha transmission wavelength to pass through that filter, which belong to this region of the sun. So this one, for example, is one of the photos, H-alpha photos of the sun. The third layer of the atmosphere is corona. So corona extended to millions of kilometers outside of the sun. Its temperature could come to 1 to 2 million degrees of Celsius or Kelvin, very different, mostly because of the magnetic activities which we have at there. So the magnetic activities accelerate particles, or sometimes transfer energies, and they hit that part to a degree of about 1 million to 2 million degrees of Celsius. This layer of the sun, we can see it during the total solar eclipse. It's somehow, its luminosity is equal to a full moon, so it's quite bright, so it could give us some kind of the light even during the a total eclipse, or we can see it using a specific device which we call it coronagraph, by hiding the first layer of the atmosphere of the sun. So this is the simple shots of different layer of atmosphere, which I'm not going to go through. Yeah, the temperature, as I mentioned, it changes a lot, drastically change. So this the photosphere temperature is something like 6,000 degrees of Kelvin. In the chromosphere, it's increased and could come to 20,000 degrees of Kelvin. And when it's come to the corona, it goes up to something like 2 million degrees of Kelvin. But something which is interesting is the density. The density in this sun atmosphere is very low. So, for example, the density of air is something like 1.2 kilogram per cubic meter. And you can see here, even in the photosphere, that one is 10 to the power minus 4. Something like 1,000 times less dense than the Earth atmosphere. And when it comes to the corona, the density of the gas at there is even lower than the highest vacuum which we can have on the Earth. Corona has four interesting features. One of them is coronal loops. So as I mentioned, the sunspot are has some kind of the bipolarity, north and the south, and those bipolarity creating some kind of the magnetic field, the loop magnetic field like that, with energy somehow trap inside, the magnetic energy trap inside. Those coronal loops could extend it to something even 1 million kilometers above the surface of the sun, and could contain a lot of hot gases and a lot of energies, and we call them coronal loops. Another thing which we have in the corona, we call it solar flare. Sometimes a lot of energy trapped inside of the coronal loops, and since those coronal loops are let's say dynamic, they are not something static, so they twist it and they suddenly trap a lot of energy, and suddenly those energy released in the short period of the time and generate some kind of just a drastic explosion on the surface of this above the surface of the sun, mostly in the corona region. and we can see them hover by using the satellite. Even through the air, sometimes it's happened that people could saw those solar flares when they did the photography. So those flares generated lots of, let's say, fast particles. There are some kind of the, let's say, relativistic, let's say, some relativistic particles which travel with the speed of the light or near the speed of the light, as well as generate a lot of, let's say, radio frequencies, X-ray, and the gamma rays. Those flares classified as A, B, C, M, and X. Which the X is the most, let's say, intense one, and the A is the weakest one. And usually for measuring of the intensity of those flares, we do some observation by measuring the X-ray, which come from the sun, at the region between 0.1 to 0.8 nanometer region. The third, let's say, feature of the corona, which is very also interesting, is the coronal mass ejection. So usually, as you saw, those corona holes hold a lot of lots of masses or gases inside of themselves. And sometimes when those explosions happen, a lot of big masses of the gases released, and they push outside, or they say explode, and they move move toward the move away from the sun. Usually the speed is something between 1,000 to 300 to 3,000 kilometers per second, something like 1,000 times to 10,000 times of the speed of the supersonic spacecraft. The amount of the energy, the amount of the, let's say, matter which also released through its CME could be huge, could be something like 10 to the power 12 kilograms, something like 1% of the mass of the Everest. And as I mentioned, they are very fast, they are particles, and they expelled out to the outer part of the sun. I'm going to pass this part because it's I already explained it. The fourth thing which we have from the corona is something which we call it solar winds. It's the usually constant stream of charged particles, mostly electron, protons, and the alpha particle, which could be helium, let's say, particle, or helium atoms, which constantly release from the sun. So they have the speed something between 300 kilometer to 800 kilometer per second. They have some kind of the constant flow, so the flow doesn't changes a lot, except if some kind of explosion happen. And since this the speed is not very high, and since also the sun rotated with the highest speed, something like that, 1 kilometer per second is the rotation on the speed of the sun, they pattern, or let's say the output pattern, have some helix pattern. It's not something direct, so they travel in the helix, let's say, a feature or helix shapes, and they're traveling toward the outer, let's say, solar system or solar system planets, and they generate something which we call it heliopause. So as I mentioned, the corona part of the sun is one of the most interesting parts of the sun, and that part of the sun is very dynamic, and it's very interesting to see that those dynamic region of the sun also, the activities changes over a period of 11 years. So there is some good correlation between the sunspot numbers and those activities on the surface or on the or inside of the corona. Okay, so the next part which is interesting is that we have something which we should call it sun-earth connection and earth and space weather. So sun is somehow for us is the life and the source of the energy. So we have a strong connection with sun. So to understand those energies or transfer, which is mostly physical processes from the sun to the earth, we have something which we call it sun-earth connection. So in sun-earth connection, we study the response of the earth mostly in magnetosphere, mostly in ionosphere and the atmosphere, based on the amount of the energy or based on the energy which comes from the sun. So sun sends us light as well as particles. The amount of the light which we receive from the sun and the upper atmosphere of the earth, or at the end of the atmosphere of the earth, is about 1.3 kilowatt per square meter. That energy generates heat for us, life for us, also ozone for us, ionosphere for us, and also we receive a particle from the sun. Those generate auroras, magnetosphere, and some anomalies. So as I mentioned, we have something which we call the solar constant. Solar constant is the amount of the energy, I mean the radiative energy which we receive from the sun. It's about 1.3 kilowatt per square meter. When that light comes, most of that light is somehow reflected back, somehow absorbed through the atmosphere, and we receive something like 340 watt per square meter on average. That energy give us the life and help us to continue our dynamic and help Earth to have its dynamic processes. But we have something else which we call it a space weather. So all of you know that we have a weather. So weather is the situation which we have inside of the Earth atmosphere. But we can define another region, a region between the sun and the Earth. So the space weather describe and talks about the situation, mostly those active situation between Earth and the sun, and mostly focus on the magnetosphere, which I'm going to discuss about it. So because of the solar, let's say, winds, those constant particles which comes from the sun, because they are the charged particle, therefore because they are traveling, so any traveling charged particle could generate a magnetic field. So they are associated with a magnetic field. So those solar wind has a magnetic field. When they come and they reach to the Earth, they somehow, let's say, interact with the Earth magnetic field and generate a region around the Earth, which we call it magnetosphere. So those magnetosphere has a shape like the oval shape, like this. The shortest part is the side which is toward the sun, has something like 10 of the Earth's radius, something like 60,000 kilometers this distance, and the tail is very big. They have a big tail, the magnetosphere, of about 400 let's say 1,000 kilometers. It's reached to the moon. So when the solar particles reach to the Earth, those particles somehow expelled by the magnetic field of the Earth. So if the Earth doesn't have any magnetic field, or if we couldn't live on the Earth, because all those let's say energetic particles, especially in CMEs and the corona and the flares, could destroy all the life on the Earth. But that magnetic field and the magnetosphere somehow save us from the let's say solar particles. Usually all the activities and the dynamic happening inside of the region called a space weather. So the space weather is dealing with all the activities, mostly radiation and the magnetic activities and particle activities inside of the magnetosphere. Usually for the space weather we have different parameters to consider. One of them is that the radio flux from the sun, which we measure. So if some kind of the flare especially happen, we'll receive a high flux density of the radio frequency at 10.7 centimeters. So it's indicated that something happened on the sun, on the surface of the sun. We have also some magnetometer, because as I mentioned, those solar winds or those CMEs carry the magnetic field by themselves, and when those magnetic field come and interact with the Earth magnetic field, we'll have some disturbances or some kind of the anomalies on the magnetic field measurement or magnetic intensity measurement on the surface of the Earth. We have two indexes for this thing. One of them is DS index, which is related to some magnetic anomalies or magnetic, let's say, ground-based magnetic meter anomalies, which are near the equator. And we have also the KP index, which is between 0 to 9. It's related to 13 stations of the magnetometers in different, let's say, mid attitude of the Earth. And it's related to the perturbation in the magnetic field which they measure. And usually if the big geomagnetic storm happen because of a CME, we see a big changes in those KP indexes, and we usually come to something like KP8 or KP9 if a big storm happen. So as I mentioned, the geomagnetic storm usually classify also based on the G1 to G based on the KP index, and they are between G1 to G5. For example, the April, the May aurora, or the May 2024 aurora which we have generated some kind of the G4 let's say geomagnetic storms. We also could measure the solar radiation, especially particles, especially using some satellite. By measuring those particles, also we can talk about if any issue happening in the space weather, and also we can do some kind of the X-ray measurement, which those mostly happen by a satellite, geosatellite. And by measuring those X-rays flux, also we can see if any, let's say, magnetic, any kind of the solar activities happen, especially flares, and if the space weather is going to be deteriorated or not. So here I try to, let's say, summarize most of the effect which we could have because of the magnetic storm or because of the space weather anomalies. So the space weather anomalies has a lot of impact on our modern life. For example, those space weather anomalies or changes could affect on the ionosphere current or ionosphere intensities, especially if the UV and the X-rays which coming from the which generated in the flare explosion could causing some kind of the scintillation in the ionosphere, could causing some kind of the absorption in the also ionosphere, and therefore if you have the radio wave kind of the communication, those radio wave communication could be disturbed or could be somehow blackout happen. It also could causes on the astronaut, if there's any astronaut outside of the Earth, especially outside of the atmosphere, if any kind of the explosion happen, those astronauts could be exposed to the high intensity of the light, especially X-ray and UV, could be dangerous for them. Could be effect on the satellite, about the satellite we discuss more, and could also induce some currents on the line, in the power line or the telecommunication line, and causing some issues. For example, in 1989, if I am right, a big explosion on the sun happened, and it generated a big magnetic storm, and that big magnetic storm induced a huge current on the lines, let's say power grade lines, and one of the transformer in the Hydro-Quebec one, if I'm right, exploded because of that extra current which generated on the power lines. It also could cause some corrosion on the pipeline, for example, when those magnetic storm happen or those particles come to the Earth. Could also affect on the rain, on the weather, but that one is not a very issue to discuss about. One of the space biggest effect of the space weather could be on the satellite performances. So when an explosion happens on the sun, something like this one, a coronal mass ejection, could cause different thing for a satellite. One of them is that because they are the charged particles, they could come and they sit on the solar panel of the, let's say, of a satellite, and causing some surface discharging. If there are very energetic proton or electron, especially protons, which generated during the failure times or failure time, they could come and go inside of some chips of the or some electronic board of the satellite and causing some problem like degenerated dielectrics, or causing something which we call it single event upsets. Another thing they could cause is that when a magnetic storm happens, the upper layer of the atmosphere get hot, and therefore is somehow expanded. And when it's expanded, it causes some effect which we call it a spacecraft drag. So a spacecraft will hit or will see more air when they are rotating around the Earth, and that drag could cause some issue to the could cause some anomalies to the let's say orbit of those satellites. It also could cause some effect regarding the radio frequencies interferences, because if they communicate with the base, the Earth base, through some radio frequencies, sometimes those explosions could cause some interferences. They could cause also scintillation happening because of the let's say ionospheric activities or ionospheric intensity changes because of the solar explosion, or they could cause also some kind of the material degradation, which because those are the let's say fast particle which bombard the surface of the satellite and could cause some degradation of the material and reduce the lifetime of the satellite. But one of the prominent, let's say, as the last part of the space weather is auroras. Auroras is the let's say well-known, let's say let's say display of the light for the people who live on the northern part of the Earth. The mechanism of aurora was not very well understood till about maybe less than 10 years ago, because recently they could 10 years, 20 years ago, they could come up with the exact modeling of what happened and how the aurora happened. But aurora usually happen when a CME happen on the sun. And if we are lucky and that CME is somehow happen, those explosions is somehow happen when the sunspot is face the Earth, but not exactly face the Earth, because it's come by the helical, let's say, trajectory. Those material or those CMEs or those coronal mass material will come and they hit the magnetosphere of the Earth, and after they induce a lot of energy to the magnetosphere of the Earth, and those energy which introduced or which is connected to the magnetosphere of the Earth causes that the lots of plasma or the particle which we have in the plasma sheet of the magnetosphere somehow get energy and start to move toward the pole of the Earth, like that, in this trajectory, and create some kind of the current ring in the top of the both south and the north pole of the Earth, somehow like that, and generate a region which we call it corona oval, something like this region, this picture. Especially the top one is the one which is happening on the May of 2024. So when those accelerated particles, energetic particles, comes to the atmosphere and they heat the atmospheric gases, mostly oxygen and the nitrogen, in the both status of the atomic oxygen, atomic nitrogen.
Dr. Naji, we are running out of time. If you can wrap it up.
Yeah, for sure. I'm
sorry for that.
My last one. It's okay.
Thank you.
So it's okay. So yeah, you are more than welcome. So when those atomic let's say oxygen or the molecular oxygen or nitrogen excited, they generated a very fantastic color or nice color, and those colors, because of the flow of those let's say charged particles, could generate a very fantastic and beautiful light. And those lights are dancing and move mostly because those particles which come from the plasma sheet also do not dance and move. This effect also could be happen in other let's say planet, especially let's say some planet, especially the planet who has the magnetic field, like for example, this one is the photo of the of the Saturn we took by the Hubble, and shows this exactly same procedure, same event on the south pole of the Saturn. Okay, so yes, I have to wrap up my presentation, but maybe at the end right now we have a little, very little better idea about that. What is the sun? What is the effect of the sun on our light, and why the sun is very important for us. Thank you very much. And this is my reference.
Thank you very much.
You're welcome.
Good evening, everyone. My name is Hector. I am a second-year astrophysics student at York University. Yeah, thank you so much, Dr. Naji, for coming on tonight and telling us about the wonders behind the most important star and vital source of life for us, the sun. Now we have a few questions for you. Now let me start with mine. Recalling what you mentioned about civilizations, let me ask you, are there any common themes or difference you have noticed in some legends across different civilizations?
Dr. Naji, you're muted.
Yes, sorry. You have my voice? Thank you very much, Hector. I appreciate it, and thank you for your question. So yes, sun is very important for all of us because the life is coming from the sun. So all the ancient civilization knows that sun has a very important role in their life. Therefore, for most of them, sun has some kind of deity position. So when we look at the different culture and the legend, to see that, okay, yes, there's a common thing, and that one is the high position of the sun as a god most of the time. But the differences which we see is that depend on the culture. In some cultures, the view toward the sun is more scientific. They use the sun for some kind of the calculation, for example, for calendar, for measuring the time. In some of them, the sun has more artistic, or let's say fictitious position. So that is the difference between the two cultures, or different cultures.
All right. Hello, I'm Zach. I'm a first-year astronomy and astrophysics student here at York, and my question is, why do we not see any sunspots at the poles of the sun?
Nice, good question, Zach. Thank you very much for your question. So it's mostly back to the dynamo effect, because as you saw in the previous slide, maybe I should back to the slide. Let's see if I can back to the slide. We have something which we call it the dynamo effect. In the dynamo effect, here. The differential rotation is happening mostly because of the differential rotation between the equatorial region and the polar region. And usually the differential let's say rotation of the sun is less prominent in the polar region. That is more prominent in the equatorial region. And therefore, since this is less prominent in the polar region, therefore those, let's say, local magnetic field, the chance of generating those local magnetic field on that region is less, or those magnetic fields, local magnetic field, are not generated at there, and they are mostly generated in the region near the equator, not near the, let's say, polar region. So it is back to mostly to the differential rotation of the sun, which is not very huge in the, let's say, polar region.
Okay, thank you, Dr. Naji.
You're welcome.
Hello, my name is Dave. I'm a first-year engineering student at York University. My question is, how does solar radiation affect Earth's climate and weather patterns over both short and long time scales?
Good question. Thank you very much, Dave. So we have two kind of the variation. Mostly when it's come to the weather, this is solar or the sun radiation energy is important. So by changing the number of this sunspot or the sun activities, the solar constant could be changed by a fraction of the percent, not more. So those fraction of the percent usually cannot have any let's say significant effect on the weather. Therefore, when we are in the maximum solar let's say spot, or when we are in the minimum, let's say the flow of the sun, or let's say in the solar radiation intensity doesn't change a lot. So we don't have a lot of variation in the climate, so in short term. But when it's come to the long term, in long term, people said, okay, there are some chances of the big variation in the solar energy as well as this solar output energy, especially the radiation energy. And when we said long term, it means that something in order of more than 10,000 years. And those long-term changes could have some effect on the weather and could cause some kind of the climate changes. But in short term, no, it doesn't have any big effect regarding the variation. Yeah.
Thank you for your response,
You're
Professor.
welcome.
Right. Well, everyone, you have been listening to the Allen Carswell Observatory's monthly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening were Cam, Dr. Alireza, Paul, Deb, Zach, and myself, Hector. Make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. All of our programs are free. If you would like to make a donation, see our website at yorku.ca/science/observatory/. You can always connect with us on Instagram with the handle @York Observatory and check out our website for show notes, content, dates, and contact info at yorku.ca/science/observatory/. Thanks for tuning in. Clear skies and have an excellent night.